I'm always a little puzzled why young people, and I notice many of you are young people, don't get a little more disturbed about this issue, because you are really the ones who are getting the short end of the stick. These are maps of the monthly temperature anomaly for approximately the last year. And the red areas are warmer than normal, where normal was 1951 to 1980, and blue is colder than normal. So you can see red areas tend to predominate. And if you looked at the United States, you'd find that the monthly average temperature, I think I counted, there were 6 months that were red, quite warm, and 3 that were blue, and 3 that were kind of normal. But if you look at a longer period of time, like a season, these are the last 12 seasons, then it turns out there were 8 seasons that were red, and 2 that were blue, and 2 that were normal. And if you look at the last 12 years, then there are 10 of them that were red, and 1 blue, and 1. So if you average over bigger times, then the weather fluctuations tend to. And why are we worried about it? Well, for one thing, there's additional global warming that's in the pipeline. It takes the climate system time to respond to the changes in atmospheric composition. There's another 1 degree Fahrenheit warming in the pipeline due to gases already there. And then there's at least another 1 degree Fahrenheit warming in the pipeline due to the power plants that are already in existence and are not going to be turned off immediately, even if we decide to do something about the problem, and the vehicles on the road, that we're not going to take off the road suddenly. So there's 3 times the amount of warming that's already occurred if you count what's in the pipeline. And that's why we need to start to deal with the problem now. And then just one more map. This is the temperature anomalies relative to 1951 to 1980 for the first 5 years of this century. The nature of this warming makes sense. It agrees with what we expect and what we calculate in the global models. For example, the warming is larger over land than it is over ocean, because the oceans have thermal inertia and it takes them longer to respond to the forcing that we're applying. The warming is greater at high latitudes than it is at low latitudes, because there are positive feedbacks that amplify the impact of the forcing at high latitudes, especially snow and ice, which tend to melt as it gets warmer, and that makes the surface darker and absorb more sunlight. And the warming is larger in the northern hemisphere than in the southern hemisphere, because there's more ocean in the southern hemisphere, and especially the southern ocean mixes heat deeply, so it hasn't warmed up much in the southern ocean. Essentially all the countries in the world agreed in 1991, 16 years ago, in this framework convention on climate change, that we should take actions to stabilize greenhouse gas emissions at a level that would prevent dangerous human-made interference with the climate system. So you would think that, since we need to define what is dangerous level, that would be a hot research topic, but it hasn't actually been a lot of papers. In fact, I submitted one in 2005, which I'm still trying to get published. There seems to be a reluctance to quantitatively address this problem. But I have my opinions, and my list of metrics for what would constitute dangerous starts with the things that are irreversible. And one of those is extermination of species, which is some scientists euphemistically call reduction of biological diversity. But that is obviously irreversible, the extinction of species. And ice sheet disintegration and sea level rise, for all practical purposes, is also irreversible on any human time scale. It takes many thousands of years to build the ice sheets. And there are important regional climate changes, which I'll talk briefly about. One of the problems is that as the planet gets warmer, plants and animals which are adapted to and can survive only in specific climate zones attempt to migrate to stay within their climate zone if the climate changes. And another region that we're in danger of pushing species off the planet is the alpine areas, which are particularly biologically diverse, the slopes leading up to the mountains. And as the temperature line, as the planet gets warmer, a given temperature line moves up the mountain. But when that happens, of course, the area gets smaller and it gets rockier and the air gets thinner, and in effect we can also push off the planet the species in alpine regions. But even in other regions, the animals and plants attempt to migrate as the climate changes. I got this email from a man in Arkansas who noted that he had never seen armadillos before, but he drives this 40-mile route, north-south route, and he's noted that they're moving further north. Well, the armadillo has been around 50 million years, and I think he's a pretty tough critter, so I suspect that he will probably survive. Homo sapiens have been around, 150,000 years or something. I guess the predecessor, Homo erectus, maybe 2 million years. But many species will have trouble, partly, I mean, at this time, the stresses on different species, animal species, are probably more due to other things that we're doing by taking over the planetary surface. But most experts agree that as we go into this century, the big stress on species is going to come from the combination of the stresses they already have plus climate change. And one way we can partly quantify this is from looking at the rate at which a given temperature line is moving poleward as the planet gets warmer. If we look at the last half of the last century, the poleward migration of isotherms was averaged about 12 kilometers per decade. Well, but in the last 3 decades, if you remember my first graph, the last 30 years, temperatures really started going up quite rapidly. And the rate of movement of an isotherm has been more like average 38 kilometers per decade. If we follow business as usual scenarios, which energy departments tell us act as if it's a God-given fact that we have to follow business as usual and continue to burn more and more fossil fuels each year, if we do that, the rate of isotherm movements is likely to be of the order of 60 kilometers per decade. It's hard to say what the impact of global warming on the number of species will be. There have been some attempts to estimate that. One source of guidance is the history of the Earth. There have been several large, rapid warmings in the Earth's history. The most recent one, large one, being 55 million years ago at the Paleocene-Eocene boundary, when the global warming was probably about 6 degrees Celsius or so, and more than 90% of the species on the planet went extinct with that warming. The second irreversible impact of global warming that I like to focus on is sea level and the potential melting of portions of Greenland and Antarctica, specifically West Antarctica, is the portion that is most unstable. The reason we're concerned, we've become very concerned about Greenland, is we note that the area on Greenland that has been experiencing melting in the summer has been increasing These maps show the area of melt in red in 1992 and 2002, and the 2005 broke the record of 2002 with still larger area of melt. The thing about the surface, this is a photograph on the surface of Greenland. During the winter, the mass of Greenland increases, and then during the summer and fall, it decreases. But over this time period, it lost mass at a rate of about 150 cubic kilometers per year. And we also notice, there are these seismometers located all around the world which are used to detect earthquakes at different and to locate and measure the magnitude of earthquakes that occur any place in the world. And they've started to find earthquakes occurring on Greenland. These are in fact ice quakes. What happens is a piece of the ice sheet will surge forward down slope toward the ocean, and then it grinds to a halt on the solid Greenland surface, and it's registered as an earthquake with some magnitude someplace between 4.6 and 5.1 on the Richter scale. But the number of these earthquakes on Greenland doubled between 1993 and 1999, and since then it has doubled again. Gravity satellite shows that the West Antarctic ice sheet, even though, as I showed on the earlier map, the warming there is very minimal so far, in part because of the ozone depletion, but we expect it to increase. But the mass of the West Antarctic ice sheet has also been decreasing at a rate of about 150 cubic kilometers per year, which, you add those two up and it comes to less than 1 millimeter. You spread it all around the world and it's less than 1 millimeter of sea level, but it has caused the rate of sea level rise, which in the last century was about 15 centimeters, at a rate of about 15 centimeters per century. And the last 25 years or so it went up to 25 centimeters per century, and in the last dozen years that we have very precise measurements from satellites, it's about 35 centimeters per century. So it is increasing, and it's just a very nonlinear problem. The danger is that we could push these to the point where we get a rapid collapse of most likely West Antarctica and also the southern half of Greenland. With so-called business as usual global warming, business as usual 2% per year increase in fossil fuel use, we would expect at least 3 degrees Celsius global warming. The last time the world was 3 degrees Celsius warmer was a few million years ago during the Middle Pliocene, and sea level then was 25 plus or minus 10 meters higher than it is now. That's 80 feet. And at increasing rates, and the disintegration of an ice sheet is a wet process, unlike the growth of an ice sheet, which can proceed only at the rate of snowfall. It's limited by the rate of snowfall in a cold place. And we know from the Earth's history, if we look at the last time an ice sheet disintegrated, was the Laurentide ice sheet in central Canada 14,700 years ago. And sea level then, during meltwater pulse 1A, sea level went up 20 meters in 400 years. So that's 1 meter every 20 years. So when an ice sheet disintegrates, it can disintegrate very rapidly. If we had sea level of that increase of that magnitude, it would have dramatic consequences on the east coast of the United States. With a 25-meter sea level rise, the entire country of Bangladesh would be underwater, and 250 million people in China. So it's really something we don't want to contemplate. And just to say one thing about regional climate change, it used to be that we would only say that, well, the extremes of regional climate will increase as global warming increases, because we couldn't really say with the patterns. But now there's one thing that all the models agree on, and it also makes physical sense. As you have more global warming, you get more evaporation from the ocean, and the tropical rain belt, intensity of rainfall increases. But also the counter part of that is the subtropical regions, the atmosphere becomes more stable. And that has implications for at least two regions, one of them being the western half of the United States and one being the Mediterranean region, where both of which we expect decreases of precipitation on the long run. And because temperatures will be going up, particularly in these regions with less rainfall, it's going to be hotter and drier in these regions. And I think, we're beginning to see the first small steps in that direction already. And again, also the history of the Earth. If you look at paleoclimate records, there is a strong correlation between global temperature and drought in the western United States. So I think there's a danger of really having super drought in the U.S. West if we follow business as usual and have large global warming. And one thing that implies is more forest fires, and with the higher temperatures, it will be very damaging to the forests. I think there is some evidence that forest fires are beginning to increase. Now let's look at the history of the Earth. This is the temperature in Antarctica as obtained from an ice core. Antarctica is a couple of miles thick ice sheet formed by snowfall piling up year after year, and it's too cold for it to melt. And so as it gets thick enough, it compresses the snow at a depth of about 100 meters to ice, and the ice traps bubbles of air. If we drill a core through the ice sheet, we can sample the snow that fell as a function of time, and we can sample the composition of the air in those bubbles and determine the composition of the Earth's atmosphere over this time period. And you can see that this is the temperature which varies by about 10 degrees Celsius in Antarctica between the warm interglacial periods and the depths of the ice ages. Now, the time runs from left to right, and we've been in this relatively warm interglacial period, the Holocene, for almost 12,000 years now. That's the period in which civilization developed, and it's been a relatively warm climate. These cycles where it gets colder over 100,000 years and then suddenly gets much warmer and then it repeats, these cycles are related to changes in the Earth's orbit. As you may know, the Earth's orbit is perturbed by Jupiter and Saturn, and because they're so heavy, and Venus because it comes very close, and it causes the tilt of the Earth's spin axis to wobble by plus or minus 1 degree. It's tilted now at about 23.5 degrees, but that wobbles, and also the orbit is not perfectly circular, it's elliptical, and the degree of ellipticity changes with time. And the date in the year at which we're closest to the sun cycles through the entire season in about 23,000 years. But one thing we can do with this is compare the current Holocene interglacial period with the last ice age 20,000 years ago. And by the way, the bubbles of air tell us that the composition of the atmosphere was changing with these same cycles. When the planet was warmer, there's more carbon dioxide and more methane in the atmosphere. If you compare these curves very carefully, you'll find that the temperature tends to change first by several hundred years. It's almost simultaneous. If you try to lay these on top of each other, they would look like they were congruent. But there is a slight lag, so the temperature change, in effect, is causing the Earth to release more CO2 and methane. But on the other hand, the CO2 and methane are one mechanism for the temperature change. They contribute to the temperature change. It's not the only thing that affects the temperature, and they're doing it as a feedback. Average temperature changes in these swings from ice ages to interglacials tend to be about twice as large at the poles as they are on the global average. They tend to be 3.5 or 4 degrees at the equator, 5 degrees on global average. We can actually now look at other points in time because we have a sea level record. We have more than one record, and they differ somewhat from each other, but they all show that the variations are typically 100 meters between a glacial and interglacial period. And this is a record of sea level change over the last 400,000 years. And so we can calculate the climate forcing as a function of time due to the change in the ice sheet area for this entire 400,000 years. And we can also calculate the climate forcing due to the change in methane and carbon dioxide. The two principal mechanisms for causing the temperature change during that 400,000 year period were the changes in atmospheric composition and the changes of the surface properties. Those were the mechanisms. The instigator, very weak forcing, was the changes in the Earth's orbit. But then these powerful feedbacks, changes in atmospheric composition and the ice sheets on the surface, amplified the effect of the very weak forcing and caused large climate changes. Well, now those mechanisms which were forced by these small changes in the Earth's orbit, those mechanisms are now totally under the control of humans. If you look at the greenhouse gases, they're now going off the scale that existed during the past 400,000 years. Those are due to human. I've greatly expanded the time scale on the right side of this diagram. There's just 150 years on this right side, so I had to magnify that so you could see what's happening. But humans are now in control of the atmospheric composition. And ice is melting all over the planet. So both of these mechanisms for temperature change are going in the same direction, and they're under our control. And if we look at, and then one of the questions is, well, how big does the temperature change have to be before it's dangerous? Well, again, I think looking at the Earth's history is our best guide. And this is the temperature at some very important regions on the globe, in the warm pool in the Western Pacific and in the Indian Ocean. These are important because those regions are the source of heat that's transported to higher latitudes, both by the atmosphere and by the oceans. And so they're a good indicator of the status of the planet. And you can see that, again, I've greatly expanded the time scale on the right, but you can see that the warming in the last 130 years has now brought the temperature within 1 degree or less of the warmest periods in the past. This is now 1 million years.